Okay, so for FRQ number 4, we are given a potential energy diagram of a block oscillating on a spring, and the x-axis represents the length of the spring. So part A asks us to determine what is the equilibrium length of the spring, and how do you know that this is the equilibrium length. So based on the graph, I know that the equilibrium length is 20 centimeters because at this point, PE is 0, and at equilibrium, the block has a potential energy of 0. So that's what I'm going to write. So the equilibrium length of the spring is 20 centimeters because at equilibrium, the potential energy, the PE, is zero. And according to the graph, PE is equal to 0 at x equals 20 centimeters. That's my answer. Okay, part B asks us if the block's turning points are 14 centimeters and 26 centimeters, draw a line that indicates the total energy. And so it wants us to copy the graph onto our paper. So let's see. 20, 15, 10, 5, and then this should be 0. This is the PE axis energy in joules. This axis, so we have 20, 24, 28, 12, and 16. Okay. And this axis is the x-axis that represents the length in centimeters. Okay, so the graph looks something like this. Alright, so this is what the graph looks like. And it says that the turning points are 14 centimeters, which is right here. Somewhere right there. Oh. $14 centimeters. And 26 centimeters, which should be right here. So at this point, I can see that it's a little bit above 5, but it's below the midline between 10 and 5, which is 7.5. So this line, or this amount, should be I'm gonna estimate 6.5. So my total energy should be equal to 6.5 joules according to this line. Okay, there. That's part B. Now part C wants us to on the same graph in part B, draw the kinetic energy graph. Okay, so I'm not gonna draw it in the same graph, but I'm gonna make a similar graph. So let's see, because I already have things, a lot of things on here. So energy. All right, and here's our graph of, this is our PE graph. Should hit 6.5 somewhere right here. All right, so this is our PE graph. And since I know that my total energy is 6.5, I know that my KE graph, which should be the opposite of this, should not exceed this line where it is 6.5. I also know that my KE graph is exactly the opposite of my PE graph. So since these are the turning points, I know it will start right here at 0, and it will hit this mark, this 6.5 line at 20, and then return back to 0 at 26. So this is my KE graph. Oops. So it looks like the exact opposite, and that since total energy is 6.5, the KE graph is limited to be below 6.5. So there we go. Okay. So part D now wants us to calculate the spring constant. Okay. So to do that, I can. So first of all, I'm going to first convert my my equilibrium length into meters. So my x at equilibrium I found to be 20 centimeters, but I'm going to convert this to 0.2 meters. Now in my calculation, I'm gonna use one of the length at which the spring is gonna turn. So it's I'm gonna use either 14 centimeters or 26 centimeters. I'm gonna choose 14. So x turning was 14 centimeters, and I'm going to convert it to meters, which is 0.14 meters. And so now I'm ready to do or find my spring constant. So I know that PE of spring, PE spring, is equal to 1/2 times the constant times delta x squared. Now note that this delta x is not the same as x. It is the distance from the equilibrium point. So once I plug in my numbers, this delta x is going to be equal to 0.2 meters, my equilibrium point, minus 0.14. So that is the distance from my equilibrium point, and squared. So I know that my PE spring max at this point is 6.5 joules. So that is going to replace PE spring. And this whole term right here, which is reduce this down to 0.0018 meters squared times K. To solve for K, I divide this to this side, and so K ends up being 3,600 or 3,611.111, and then my units is newtons per meter. So that is my constant. So once I divide that, that's what I got. Okay. Part E wants us to determine the maximum kinetic energy. Well, this is pretty easy because KE max for my block is going to be equal to the total energy that's in the system, or the total energy. And I found the total energy to be 6.5 earlier, or estimated to be 6.5. So my KE max will be 6.5 joules. Okay, part F. Part F wants us to determine the kinetic energy of the block at x equals 16 centimeters. Okay, so first of all, I'm going to convert 16 centimeters to meters, which is 0.16 meters. And now I'm going to set up this expression. So my KE at x equals 16 meters is going to be equal to my energy total minus my PE at x equals 16 meters. So now I can sub in what I know. So this is what I'm trying to solve for: KE at x equals 0.16 meters. My energy total is 6.5 joules. My PE at x equals 0.6. I'm at 0.16 meters is equal to 1/2 the constant times the constant. Constant is found to be 3,611.111 newtons per meters, and my delta x is my equilibrium position, which is 0.2 meters minus wherever I'm stretched to, which is 0.16 meters squared. So that is my expression for what PE at x equals 0.16 meters is. So reducing all of this, KE at x equals 0.16 meters, all of this combined is going to be equal to 3.611 joules. So that is my energy, my kinetic energy at 16 centimeters. Okay. Part G wants us to ask us what will be the turning points if the kinetic energy, if the block's total energy is doubled. Okay. So if the energy is double, the energy total new, that is new, is going to be so double of the energy total initial, which is 6.5 joules. And so this turns out to be 13 joules as my new total energy. So now my so if I want to find my new turning points, what I have to do is set my PE at my turning point equal to my total energy new, because at the turning point all my energy goes into the PE spring. So PE spring at turning point is going to be equal to energy total new. Okay, so my PE, so my PE turning point, my turning points, I'm gonna call C. So this is P at x equals C, and my energy total new I found to be 13 joules. Okay, so PE at x equals C is equal to 1/2 times just the constant, which is 3,611.111 newtons per meters, times delta x squared. My delta x squared is, or my delta x is the equilibrium position, which is 0.2 meters, minus however the position that it's stretched to, which is C, or compressed to. So minus C, and then square, and that's equal to 13 joules. So now this right here reduces down to 1805.556, and this all stays the same. My C squared is equal to 13. Okay, so I want to solve for C. What I'm gonna have to do is divide this to this side. So if I divide 13 by 805.556, I'm gonna get, so this side, this is going to be equal to 0.0072. Now I'm going to square root both sides. So square rooting both sides, I'm gonna get 0.2 minus C is equal to, now if I square root both sides, this can be plus or minus the square root of 0.0072. Since it's plus or minus, now I have two scenarios, and that means, of course, I have two turning points, so that makes sense. Now I'm going to solve for, well, I'm gonna isolate for C first. So subtract 0.2 over. So square root plus or minus square root of this minus 0.2, and then times negative to everything. So C is going to be equal to, this becomes positive, and this is still plus or minus square root of 0.0072. Okay, so now I'm going to solve for both of the C's, both of the turning points. So scenario 1 is if this is positive, if this square root is positive, so C is equal to 0.2 plus the square root of 0.0072, and that's going to get me 0.285 meters, or if we want centimeters, we just times it by 100, and this gets me 28.5 centimeters. That's one turning point. The other turning point is if the square root is negative. So c is equal to 0.2 minus square root of 0.0072. Plugging this into the calculator, I got 0.115 meters, and this is also the same as 11.5 centimeters, and that is my other turning point if my energy was doubled. So these are my two new turning points if the energy was doubled.